Alright, so in this video I'm gonna be explaining another important article with the title Going Deeper into Permutation Sensitive Graph Neural Networks. This paper in ICML 2022. The invariance to permutations of the adjacency matrix, for example graph isomorphism, is an overarching requirement for graph neural networks. Conventionally, this prerequisite can be satisfied by the invariant operations over node permutations when aggregating messages. However, such an invariant manner may ignore the relationship among neighboring nodes, thereby hindering expressivity of GNNs. So we devise an efficient permutation-sensitive aggregation mechanism via permutation groups, capturing pairwise correlations between neighboring nodes. We proved that our approach is strictly more powerful than the two-dimensional WL graph isomorphism test and not less powerful than the 3WL test. Moreover, we proved that our approach achieves the linear sampling complexity. Comprehensive experiments on multiple synthetic and real-world datasets demonstrate the superiority of our model. So relational pooling in this important paper in 2019 proposes the theoretically most powerful permutation invariant model by averaging over all permutations of the nodes, which can be formulated like this. And S sub n is the symmetric group on the set, and F is sufficiently expressive. The permutation-sensitive functions, especially sequential models, are capable of modeling the k-array dependency among k-input nodes. Meanwhile, the different input node orderings will lead to a total number of k factorial different k-array dependencies. These k-array dependencies indicate their relations and help capture the topological connections among the corresponding k nodes. So the simplest way is to replace the n-array dependency with the two-array dependencies, for example pairwise correlation. Suppose n neighboring nodes are arranged as a ring. We define this ring as an arrangement. An initial arrangement can be simply defined like that, including n-array dependency and n two-array dependencies. Since a permutation adjusts the node ordering in the arrangement, we can use a permutation to generate the new arrangement, which corresponds to a new n-array dependency covering n two-array dependencies. The following theorem provides a lower bound of the number of arrangements to cover all two-array dependencies. So this is modeling our pairwise correlations between n neighboring nodes via permutation. So without loss of generality, we apply the widely used recurrent neural networks as the permutation-sensitive function. So you got the idea. Then we can conclude that equation 3 realizes the efficient approximation of permutation invariance with low complexity. But in practice, we merge the central node V into RNN for simplicity. Then we apply a readout function to obtain graph representation. So because we need this for graph classification, for benchmarks such as protein, NCI1, and also we can do it for node classification, Colab, PubMed, CiteSeer, Cora. So you see the performance for different models. They compare it with this model.